Hello community, part C of multi-agent devices. Today we still look at multi-AI agents that interact with each other, and now you had time to read this beautiful publication on the feedback in imitation learning, the three regimes of covariate shift, and of course we focused on Alice. Now, you know now that Alice uses your importance sampling to correct for the distribution mismatch. The distribution mismatch I introduced in my very last video in part B. This technique involves re-weighting the loss associated with each training sample by how representative that particular sample is of the distribution encountered under the learned policy. And the aggregated loss in Alice is, as you know now, calculated across potentially all states visited under both the expert learner policy and the learner's policy, but weighted such that the states that are more likely under the learner's current policy, that they have more influence. So this helps simply in adapting the learner to be efficient under its own induced state distribution. So this means simply Alice as a single agent iteratively adjusts the learner's policy based on the feedback that is actively requiring during these training processes and making it more adaptive to changes in the state distributions as the learner policy evolves. And in my last video I spent 10 minutes to explain here distribution and state distributions. Beautiful. So, for instance, if certain lighting conditions are underrepresented in the training data for a robotic arm, but commonly encountered in the operation, Alice helps us now to increase here the importance weights, the tensors, for the very few training examples collected under these lighting conditions, ensuring that they now have a greater influence on the learning process. So a simple idea, but a brilliant idea. Now, loss aggregation, the aggregated loss in Alice, can be tailored to emphasize the learning from situation where the model performs poorly due to environment variation. But by dynamically adjusting now the loss based on the performance metric, for example to predict the errors under different lighting conditions, Alice helps now our model learn to correct its own deficiencies. And of course we have data augmentation. And while this is not officially a part of Alice, you know, and we do it, that the data augmentation techniques can be used in tandem with Alice to generate more synthetic training data for our student that mimics various real-world environmental conditions, different shadows, different recording angles for our multi-cameras, multi-sensor arrays, and so on. Now, you understand, of course, that Alice in itself already has a certain degree of complexity. And this arises simply by the need to calculate the importance weights and to manage dynamically the adjusted losses. This can be quite intensive, especially if the dimensionality of the data, if you work with high-resolution cameras, high-resolution sensors, multiple high-resolution sensors, and the diversity of the conditions increase. So the more undefined your environment is, the more you have to invest in a good, powerful computation infrastructure. And of course, you have to be careful if you code this, that whenever you implement the Alice algorithm, this requires some real sophisticated data management. And let me make this clear, the better you are prepared and the better you are here with the data management to track all the different conditions, angle, shadows, whatever you have, under which each sample was collected, and to adjust the importance sampling mechanism accordingly, this can help you immediately, and this will improve your model performance. It also demands careful tuning to balance the model's responsiveness to underrepresented conditions without causing now instability or overfitting of your model. Now, you know that we now have corrections, and Alice integrates our correction primarily through a feedback loop where the performance on the model under operational condition is now continuously assessed. And all those little discrepancies between the expected and the real-world actual performance guide now the adjustments in important weights and loss aggregation. So ongoing learning process helps refine the importance weight and to improve here the model's adaptability. And this is what we want, that the model has a certain freedom to adapt to new environments. Now, this is the classical formula, the mathematical foundation here of Alice here. The core of Alice is an objective function that minimizes the expected value of a loss function adjusted by our importance weights. And the important weight for a state-action pair is given by the ratio of its probability under the learner's policy to its probability under the expert policy. And you know this is the classical loss function, where rho pi and rho pi expert are the state-action visitation frequencies under the learner's policy pi and the expert policy pi expert. Now, if you've never seen this, I asked myself here the first time, what are state-action visitation frequencies? This state-action visitation frequencies here in multi-agent imitation learning male refers now to how often particular state and how often particular actions are visited in the course of the interaction with the environment. So this metric is crucial for understanding the dynamics of a policy interaction with the real-world environment and plays a significant role in learning and optimizing here the behavior. Now, you can calculate the state-action visitation frequencies. You have here the formula where, of course, T represents the time step within the episode, Y is the discount factor, typically used in reinforcement learning to prioritize immediate rewards over distant future rewards, you know this. And then we have a probability P of being in state S and taking the action A at a time T following the policy pi. Now, the frequency with which certain state action pairs are visited is now crucial to understand for evaluating how effective the policy is in general. So for instance, if certain state action pairs that lead to high rewards are rarely visited, you have to adjust the policy. And I showed you in my old videos about Q learning or policy gradient methodology. If you use this in knowing the visitation frequencies, this helps to adjust the policy towards those more rewarding actions. Your gradient will indicate in this direction. If the frequencies indicate excessive concentration on certain action in a certain region in the action space that we build, the system might need to explore more diverse action to escape here some potentially suboptimal policy traps, some local minima that we want to escape, and therefore, again, exploration versus exploitation. But formally, the loss function is defined in this way. So we have now with Alice a powerful tool dating back to 2021 for addressing the distribution mismatches in imitation learning. I showed you in my last video, applying it to complex variable environments such as those involving visual data from robotic systems that require some extensive customization and computational resources. And now comes the step you have been waiting for. Now we go here from a single agent to a multi-agent, so a Malice. So Malice, the multi-Alice, takes now the foundational ideas of Alice and applies them in a multi-agent setting, where the interaction between the agents now add layers of additional complexity to the learning dynamics. Malice, what does it stand for? Multi-agent aggregation of losses to imitate cached experts. So we are still here in imitation learning, but now we take care here in our Markov game framework for multi-agent interaction that are stochastic game elements. So you might say, what? We add more complexity? Absolutely, because we have the computational power now. So Malice now, of course, it's a complex system, introduces additional complexity. Due to the need to handle now all the different interaction among multiple agents, each with their potential strategies and reactions, which are, of course, not factored in single agent scenario of our Markov game. So how do we have to adapt this? Again, in Malice, we have the importance sampling and the loss aggregation like in Alice. But they must now account for the interactions among multiple agents. So this requires modeling the joint policy and the state action visitation distribution for a group of agents rather than for a single agent. Now, specifically considers how the action of one agent affects the state experienced by all the other agents, Markov game. This is crucial in environments like cooperative games, or if you go for a competitive scenario, where the agent strategies are interdependent. Real important fact, Malice operates under the assumption that the expert demonstration, the policy, sufficiently covers here all the critical areas of the state space for all agents involved. This coverage now is crucial for accurately estimating the importance weights in a multi-agent context. But you might ask, okay, but imagine now that this is not the case. Imagine now that the expert demonstration did not cover all angles of recording something, or did not cover, daylight, or at night, or infrared, or ultraviolet light. Well, then we have here the second algorithm I'm going to show you in a minute. So, yes, you know this now. Short summary, Malice focusing on optimizing here the multi-agent policy by minimizing the regret gap of my last video, a measure of how much better any agent, could perform by not following the recommended policy by our mediator sigma. So this is particularly challenging in environments where actions of one agent might affect the outcome of all the others. Plus, we have a dynamic environment that can change unpredicted. So what is the objective function of Malice? Minimize the regret experienced by any agent due to the deviation from the policy recommendation, you remember the phi I in my last video, recommended by a mediator sigma. The mathematical formulation involves aggregating the loss over different states that the agent might encounter, weighted by how well the expert policy does indeed cover these states. Now, if you know this, consider a set of states in a joint action space from my last video, the expert policy pi sigma expert and the learner's policy pi sigma are defined over the spaces, and the regret gap, which Malice now, the multi-agent, aims to minimize, is defined exactly as I showed you here in part A of this video series. And you know all the factors. Loss function we have seen already, beautiful. Now we go from a single agent to a multi-agent loss function in Malice, designed identical to weight the imitation loss by the coverage probability of each state under the expert policy. And this here simply ensures that the learning process focusing on states that are critical according to our main expert experience, but might be underrepresented in the learner's experience, and therefore our generalized loss function in Malice can now be expressed in this particular way, where our d pi denotes now the state visitation distribution under the policy pi, and the loss term comparing the action suggested by the expert policy sigma expert at state S with the action taken at the learned policy sigma at the same state. Importance sampling, this is a particular ratio in the loss function and acts as an importance sampling term which corrects for the distribution mismatch, part B of this video, between the expert and the learner regarding the state visitation. So this term helps to appropriately scale the loss based on how frequently states are visited under each policy, emphasizing learning in states where the learner's policy deviates from the expert policy. And this is exactly what we want. We want that each of our little AI agent behaves like an intelligent agent that is allowed to deviate for a certain epsilon from the predefined expert policy, thereby defining and discovering new paths. If you now look for my green grasshoppers, they are currently the pink grasshoppers, as I just noticed. Let's talk about again the complexity, because this is really important. We do have an inter-agent dynamics. And of course, if you think about it, we have now a significantly increased state space. Because in multi-agent systems that are now managed by Malice, The state space includes not just the states of the environment, but also the states related to each agent action and each decision. So this dramatically increases now the complexity of the state action space in total that the system needs to learn from. So each agent optimal policy might depend on the predicted policy of the other agents, and this interdependency complicates the learning process further, as we know, as the policy learned by one agent can affect the outcome and thus the learning process of all the other agents. So we have kind of a perfect chaos, but we have the mathematical apparatus to solve this. Talking about solving, coordination, communications. You know that our AI pool with our agents may cooperate or may compete for certain things, but this adds, of course, layers of strategy to their interaction, which needs to be learned in the first place and then to be optimized. So in our Markov game, for example, agent must anticipate and react not just how the static environment behaves, but also to the dynamic strategy of all the other AI agent players in our defined environment. Of course, we have a communication overhead and importance sampling, loss aggregation. We talked about this. Malice must calculate here the importance weights, considering not just the individual experiences, but also the joint experiences of multiple agents acting now in this defined environment, which again can significantly increase the computational demands. Further, multi-agent loss function. You get the idea. You need a real powerful computation infrastructure for this. Again, you know, Markov game, part B of my video, Malice now, Markov games, an extension of the Markov decision process to multiple agent, are a natural framework for implementing Malice, as we have seen for Alice. And again, we have the same elements, the states, the action, the transition probabilities, and each agent receives a reward based on the current state and the action taken by all the other agents, reflecting their individual objectives, which may be cooperative or competitive. So there you have it. This Malice approach, if you take a step back, is designed to efficiently minimize the regret gap under a coverage assumption. And this is happened exactly in part B of this video, where we talked in detail what is the regret gap and how can we minimize them, what is the optimization problem we have to solve mathematically. Now the coverage assumption means that the expert demonstration adequately covered the complete action space, which allows the algorithm to estimate importance weight accurately. But you know, in real time it is different. So those multiple agents operate in a Markov game where the action influence both their own and other agents' outcome. We have the mechanism of importance sampling to adjust the learning process, and the aim overall is to minimize the regret gap and not just the value gap as in part A. Malice now, which aims to minimize the regret associated with not following a joint optimal strategy, fits now beautifully within the framework of the Markov games. Alice seeks to develop a joint policy that is optimal for a group of agents by considering here all the potential deviation of all our individual agents that might take place. The Markov game elements allow here for the modeling and the analysis of such joint policies, where the success of one agent strategy might depend on the strategy adopted by other agents. Beautiful. For the rest, all my little grasshoppers, I guess you already know this by now. So now to the second most important algorithm here in Mail. Blades. It's simple. What happens if our learner's policy discovers now that some of the experts' demonstration and the expert policy does not cover new environmental condition? So suddenly the learner needs help because the training data are not complete. For this we have blades. The second method here for multi-agent imitation learning is blades, which addresses the scenario where it might not be reasonable to assume that expert demonstration cover the complete state space effectively. Particularly interesting because it incorporates an element of querying an expert, an external expert during the learning phase. which is a powerful way to handle complex environment and agent dynamics not fully captured in the initial training data. But now this expert can be a human expert if you want, but of course it will be, in the most cases, a connected AI expert system. Great. Blade now relies here on a direct access to a queryable expert, which means during training, algorithm can ask an expert for the optimal action in states that are encountered due to deviation from the typical policy path. This helps in filling in the gaps in the training data actively. As agents explore the environment and encounter new situations not seen in the training data, now the new Blade algorithm collects this new data and query the expert for the best response. So this dynamically now enriches here the training data set with all this crucial information on how to handle here a wide variation of scenario that suddenly happen in a real world scenario that were not part of the training data set. The loss function in Blades is adapted based on the new data and the expert feedback, continuously refining the agent policies. So you see, the more unforeseen real-world conditions you put your system of interacting AI agents into, and the more they learn, the more they have access to experts that know about these special conditions, the better they will be able to operate in new dynamic environments. For my blue-green grasshoppers, okay, gee, today it's really colorful. Short summary, Blade, sophisticated approach in multi-agent imitation learning, integrates a queryable expert system to enhance the training process, useful in complex environments where agents frequently encounter situations not covered by the initial training data. You have an expert system, you have a dynamic data aggregation, you have the expert suggestions are now integrated into the training data set, your loss function is adopted, and you still have the primary goal to minimize the regret gap, ensuring that the learn policy is as close as possible to the expert policy. And this was Blade. So let's summarize Blade, the learning process in Blade. Start with your preliminary model trained on available expert demonstration, covering as much of the state space as possible, given the training constraints that you do now not have infinite amount of training data or infinite amount of hardware. Deploy now the agents in the environment. As they operate according to the current policy, monitor their performance and the states that they encounter, identify those states where the model prediction lead to suboptimal outcomes, or where the state is not well represented in the training data. Then you know that you have to do something about these situations. And now, the solution for each identified state where we have not enough good training data, query here an external expert, an AI system, whatever you have, a database, whatever you have access to for the optimal action. So this is now crucial for bringing in new information, maybe think of a RAG, for adapting the model to handle a wider range of situations much more effectively. It updates the training data set with new state action pairs. You do this continuously, periodically retrain the model on the updated data sets, which now includes the additional expert validated data entries. You have the same cycle, adaptive loss function, you notice. You repeat this process of operational deployment, monitoring, expert querying, and retraining. And this iterative cycle allows the system to continuously improve, continuously adapting to new challenges and complexities as they arise. And then, if you do this, and let's come back to the example of our Mars rover, if you do this on Earth and you have a long training cycle, and whatever obstacles you occur here, that you find and you train your system with blades, then the more perfect, the pure imitation learning process happens if we then have to transfer the learned intelligence of our expert now here on Earth to an edge device, the Mars rover. This is then a beautiful transfer, and the rover has then the possibility to continue the training on Mars in another real-world environment. So there you have it, ladies and gentlemen, we come to an end. So, short summary. In the dynamic and completely interconnected world of our multi-agent system, Mail offers here a sophisticated new framework for training agents through expert demonstration, imitation learning. This approach is crucial in dynamic environments where multiple agents now interact and where every agent decision impacts the collective outcome. We introduced 2 new algorithms, showed you the research publication, Malice and Blades, as defined by Carnegie Mellon University, stand out as innovative strategy designed to enhance the reliability and effectiveness of our learned behavior. Malice, again, detail addresses here the challenge of strategic interaction among agents by minimizing the regret gap, stabilizes the system, aligns the agent behavior towards collective objectives, leveraging the concept of regret minimization to ensure the robustness against individual deviations. Blades, focusing on dynamically enriching in the training data set in real time by incorporating expert feedback directly into the learning process, especially in those scenarios that are not covered by the initial training data. Those are the blank regions in our state action spaces. And this adaptability makes Blades especially valuable in rapidly changing environments where agents frequently encounter complete novel situations, allowing here the learning process to continuously evolve and adapt based on expert insights. And there you have it, part A, part B, and now at the end of part C, we have now the complete integration of our mail, of our multi-agent imitation learning. We discovered 2 new complete algorithms, Malice and Blade. They both mark here a significant advancement in our ability to engineer a little bit more intelligent system that can learn from one another and cooperatively thrive in complex dynamic environments. Beautiful. I hope you learned a little bit. I hope it was informative. I tried to summarize here my knowledge to my best extent. I would appreciate any feedback of any kind from you. And it would be great to see you in my next video.